Well, hello, welcome back. So over the past few lectures, we've been talking about delving into extensive properties, intensive properties, and specifically looking at three intensive properties: pressure, temperature, and volume. And we've been looking at the phase diagram for them and talking about some of the processes. And we are headed in a certain direction with that discussion. We're going to start talking about thermodynamic cycles. But before we can get into any of that, we need to come at it from the angle of energy. We need to really discuss energy because that feeds into our conversation of thermodynamic cycles. And so the next couple of weeks of lectures, we're going to be focused on energy and laws of physics that have to do with energy. So this is our topic for today. Now, energy is, in my opinion, and in the opinion of a lot of other physicists, the single most fundamental concept in all of physics. If there was one thing that you just had to understand, it would be energy. And almost everything else in physics comes from an understanding of that. So the first sort of problem that we get into before we put anything up on the board is a philosophical one. See, the idea of energy has been around for absolutely ever. And during its existence, the question has been posed, is energy real? Or is energy a made-up, nonsensical concept? After all, I can touch this stapler and feel it, right? This is real. I can move this stapler, so I know that the motion is real, right? It has a velocity, I can measure it. It's got a position I can measure. It's got an acceleration I can measure. So all of these old school physics concepts that I'm just naming are real things. And there's almost no debate over that. There was a few people, I remember Zeno, he was a Greek philosopher who debated motion being real. But let's be realistic here. That stuff is real. Understand that energy is different in the sense that I can't see energy, I can't touch energy, I can't really experience it in a way that makes it real to my senses, like a lot of other concepts in physics are, okay? Temperature, we deal with it in this class. That's something that we're all happy to concede is real, but is energy real? So, I want to put that question up here. Now, it may surprise you, it may not, to know that today, perhaps more than any other time in history, this subject is hotly debated. There is a huge field of philosophical thought dedicated to this whole conversation. And I would like to quickly move past that philosophical issue with this simple answer. I don't know, but it's useful. What I mean by that is that if energy is a made-up concept, it's an extremely important made-up concept. I want us to think of energy as a tool, maybe not as an actual thing, but as a really, really effective tool for learning about the world around us. So much of physics has come from the study of energy that there's no way that we would be able to have the field of physics that we have today without looking at this as something that we need to use. So think of it as simply, if you want, it can be a trick. If you're of that mindset that energy is just a fancy trick, that's all right. The point is, in this class, it's a trick that we're willing to use, okay? We take concepts that we have a fundamental understanding of, that we think are real, and we simply combine them and we call it energy. Let me give you a brief example. We're going to talk about this in a minute, kinetic energy. We take a half, we take the mass, that's real, and we take the velocity squared. Everybody's happy that velocity is real and mass is real. So this is all real concepts. When we multiply them though, do we get something real? I don't know. Is that a real thing, multiplying those? I'm not exactly sure, but it's useful, and so we're going to use it. All right, moving on. That's our answer. I want to talk about a fundamental concept in physics regarding energy, and that is the conservation of energy. This is a universal law of physics. Universal meaning that it applies to the entire universe. It applies everywhere in the universe, at all times in the universe. There are zero exceptions. The conservation of energy. And this law states that energy cannot be created or destroyed. Only change forms. There is today exactly the same amount of energy in the universe as there was 1,000 years ago, as there was when the universe first came into existence. The energy in the universe is not a single bit is created and not a single bit is destroyed. It is precisely the same amount. All that it does is change forms. Over all these years, over all that humanity has done to it, as when we've been on this planet, cutting down trees, creating power lines, no matter what we do to it, all we're doing is changing forms of it, okay? Now, here's the question. Well, the first question would be, what are the forms? And we're gonna talk about that, some of the different forms of energy. But there are sure times when it seems like energy is created or destroyed. So imagine that I have a system. This is my system, and it looks like, I measure it, and I make a measurement, and it looks like the system has more energy than what it started with. And I can think of lots of real-world scenarios for this, but I'm just keeping it general. Where did that energy come from? Was it created? Well, no. It came from outside the system. Remember that on day one we talked about the surroundings? If any energy enters the system, it comes from the surroundings. Always. It's sometimes hard to figure out how it got in. That's where it seems like, oh, energy's being created. No. If you think about it hard enough and study it hard enough, no matter what your problem is, you will always discover that if the energy inside of a system changes, it's either going out or coming in. Okay, so all I need to do to account for that energy is draw my bubble wider, right? If now I go like this, oh, I found it. The energy inside this system didn't change. And what if it looks like the energy in this system changed? What if it looks like this system lost a little bit? Draw my bubble wider, right? If I go a big enough system, eventually I'll find, there's all my energy. None of it's being created or destroyed. And how big does that have to be? The universe, the size of the universe, okay? So energy can leave Earth, energy can come to Earth. Earth itself is not a big enough system. There are energy changes on Earth. It's the universe. On the size of the universe, energy is not created or destroyed. It does not leave, it does not come and go back and forth. It is simply fixed. And it's changing forms all the time. That is the law of conservation of energy, and it's extremely fundamental. Another idea about energy that's really important is that energy is a relative scale. What I mean by that is, let's say that we have an energy, this would be called an energy spectrum. All it is a graph, okay? Don't get confused by the word spectrum because you've heard it in other applications. This is my energy level, increasing energy. So somebody down here has less energy than somebody up here. What I'm trying to say with the fact that energy is relative is that there is no way that I can assign where on this spectrum 0 is. I can't do it. It's fundamentally impossible. It's not just that I don't have good enough measuring tools or I don't have a good enough understanding. It's that the universe says you cannot put 0 on this scale. All I can do is measure the difference. So I can say that this difference is 5 joules. Let me show you some of the different scenarios. Let's say that this was 1 joule and this was 6 joules. All right, I've got an energy difference of 5 joules. But on the other hand, imagine this was 200 joules and this was 205 joules. I've also got an energy difference of 5 joules. Which one is right? Can't tell you. Because if I were to label this axis absolutely, it implies that somewhere down here there is a 0 point, and there's not. So the 0 point is floating. It's not defined. That means that there's no definite scale. All that there is a scale of changes. I can for sure say the energy changed by this much, whether it be going up or coming down. I can say how big the gap is, but I can't say what the values of the gap are. Now, sometimes, and actually, when I say sometimes, in our class it's going to be a lot of the time, but sometimes I will pick a 0 point because it makes my calculation easier. So I will say, let's just call this 0, and for the point of this lecture, let me put it in quotes. It's not really 0, but let me call it 0, and then we'll call this 5, right? This is in quotes because I'm the one calling it this. It's in no way actually 0, but I'm deciding, let me call it 0. And this is how energy works, okay? I can pick a 0 point, but that's not our real 0 point. It's artificial. Okay. Let me raise the board here, and we'll talk about changing forms. What are the different forms of energy that we can have? So, first of all, we have kinetic energy, translational. This is when something's moving. If I grab this and start moving it in a straight line, I've just increased its energy by moving it. Now it has a certain amount, now it has more. By moving it, I'm giving it energy. That's just moving along a straight path, okay? Translational, that's what the T is for. There's also kinetic energy rotational. Now it has a certain energy, now it has more. By spinning it, I'm giving it energy. Kinetic energy rotational. The R is for rotational. So I want to write down the formulas for these. This is 1/2 mv squared. This v I've written without the little hooks on it, and that means that I mean velocity. This one is 1/2 I omega squared. I is the moment of inertia, and omega is the angular velocity. Okay, this is from like tech physics. You guys have seen these concepts. Both of these energies fall into a category called kinetic, obviously. That's the name. And this word means that the energy comes from moving. That's the key point with kinetic energy. That's what the word kinetic means. These two types of energy, whether it's translating or rotating, it is moving. There are other types of energy. There is potential energy, and there are different forms. This is spring potential energy. When you compress a spring, you give it energy. There is potential energy electric and potential energy magnetic. Okay? These come from underlying fields in the fabric of the universe. There is, actually I won't put that one up quite yet. Tell you what, there's more, but I'm gonna hold off for just a second because so I'll write up that this is called potential. And it doesn't come from moving, okay? Forms of energy that aren't from something moving. Now, I'd like to draw, before I proceed, I'd like to draw a big, thick line right here and make a differentiation. I hope that's fairly straight. And here's what I'm differentiating. Macroscopic and microscopic. So you guys are probably familiar with what I mean by those terms. Here is anything that we can get a handle on, our experiences. The stapler example, that's something that I can experience and understand because it's macro. It's as big as me. It is roughly my size, and it's in the world I live in. Microscopic, anything that is so tiny that I have no intuition. I don't really understand what it looks like for an atom to be rotating or something like that, okay? These are the definitions of macroscopic and microscopic that you guys know and understand. Now, every single form of energy that I've listed so far is for both macroscopic and microscopic. So I would like to list, and it may seem redundant, but there's a reason, I would like to list all these again. Okay, so you'll see that these forms of energy are macroscopic and microscopic. There are both versions of them. So if I take the stapler and rotate it, there's macroscopic energy from the whole stapler rotating. There's also microscopic energy from every little single atom inside of the stapler. Now, what are those atoms doing? Okay, let me draw a diagram of an atom. So I'm going to draw it over here. Let me draw a picture. So this is going to be a cluster of nucleons. They're particles that make up the nucleus. These are protons and neutrons. Okay, and I'll label this the nucleus. Around this nucleus, there's an electron. And let's just draw a simple model where it's spinning around. Okay, this is the symbol for an electron. Then, if I want to make a molecule, I have to put another one. So I'll put another one out here, and it's spinning. And then, this would be a gas, just two atoms free floating, not connected. But in a molecule, in a liquid, right? They're bonded together. So, and then this one's bonded to the one next to it, and this one's got bonds with the one next to it. They have bonds that connect them. So this is a picture of what's happening microscopically. And so on a microscopic level, these little molecules, they can rotate and they can translate. And so they have microscopic kinetic energies. These are kinetic energies in the microscopic world. And there's a term for all the kinetic energies in the microscopic world. And it's called sensible energy. I don't know who came up with that word or why, but that's what we mean when we say sensible energy. It's microscopic kinetic energies. Oh, there's another one. The rotational energy of this electron flying around. That's rotating, okay? That's sensible. Now, another thing that this molecule has is it's got bonds between it. These are the bonds that I drew in, and they act like little springs. What they really are their electromagnetic forces in between, and that gives it energy. And so when we break down the bonds between here, we release what's called latent energy. So latent means anything to do with a phase change. Remember that if I break down those bonds, I'm switching phases. I'm going from a liquid or solid or whatever it is into the next phase, like solid to liquid, liquid to gas. I'm crossing a phase transition. And the energy that I'm releasing by breaking those bonds when I cross the phase transition, that's called the latent energy. There's another form of electrical energy here. So I've broken these, okay? Picture these broken. Now these are two free-floating atoms. Well, this electron and this nucleon, these nucleons here in the nucleus, they have energy between them. This electron doesn't want to fly off on its own. It wants to stay revolving around. Remember that I defined the word plasma. Plasma is when these electrons do what's called ionize, and they do break away. That takes more energy. I have to break these bonds. So it's like chopping the electron off from the nucleus. That is called chemical energy. And so all of these, the microscopic versions of them, it's mostly electromagnetic, and they're modeled as springs, which is why I include springs. This is called latent energy. That's the big bonds between the molecules. And chemical energy. Chemical energy are the bonds between the electrons and the nucleons within the atom. Now, that leaves us with one more type of energy. And it is the energy between the individual nucleons. I drew a bunch of little particles in there making up that nucleus. I could try to rip those apart. That takes the most energy yet. It's incredibly energy intensive because they're held together really tightly. But if I rip those apart, that type of energy that's holding them together is called nuclear energy. So that's where you hear the buzzword nuclear energy all over. That's what it is. And it's on my list of microscopic energies. It's potential energy nuclear, N for nuclear. This is nuclear energy, all right? Now notice that nuclear energy is not on my macroscopic list, okay? That's because nuclear energy is unique in that it's only microscopic. There isn't a macroscopic version. And there's actually one that's only on this list, which is gravity. Potential energy from gravity. It only appears in a macroscopic version. And there's a fundamental reason why this is only here and that's only there that I don't want to get into, all right? But now, this is a pretty full list. These are all the different types or forms of energy that I can have. Okay, so sometimes it is useful to do this. It's kind of wild. Watch what I'm going to do. I'm going to draw a big lasso around all these forms of energy right here and collect them all up. And I'm going to say that whatever amount of all this energy is in my system, I'm just going to give it one symbol and call it U, which is the symbol for internal energy. You can see in the word how it's cheating. All this little delicate stuff is happening on the internal structure. These are bonded to those are bonded together. The whole thing is moving and flipping and moving through space, but I don't care about any of those details. All of these types of microscopic energy, I'm just going to throw one letter on it, slap it on, and say U. Internal energy. And then, that whole collection, I can actually move it up here onto this list. Okay? So internal energy, it's a macroscopic way of including all this in. So we only have to talk about macroscopic energies. It's like saying, well, this is kind of messy. All these little ones down here don't fit on our list. Let's just call them all one thing, and then boom, we can smack it on our list. That's what internal energy does, and we give it the symbol U. All right? Couple last things to talk about. With both regular energy and internal energy, we can define, remember that they're extrinsic. extrinsic. That means they depend on the size of the system. If I took my system with a certain amount of energy, cut it in half, I would also have the energy. So these are extrinsic. But we can define versions of them that are intrinsic using the same trick. We divide by the mass, and we call it the lowercase version of that letter, and we call it the specific energy. It's just like we did with volume. It's just like we did with, what's the other thing that we had a specific version of? There was something else, but there's specific entropy, specific enthalpy, specific Gibbs free energy. So there's lots of other things. I think we've seen this for something else too, but we do the same thing here. Little u is big U over m, and this is specific internal energy. So if you see these little lowercase letters, that's what it means, and these are intrinsic. Remember that we like to deal with intrinsic quantities when we can. Okay, so these no longer depend on the size of the system. When we talk about energy transfer, here's going to be my system. I have a box, and I have energy out of my system, and I have energy into my system. So there could be even, right? All I'm saying is I could put it in or take it out. There's a difference here between what physicists do and what chemists do. And this is interesting. Chemists will put themselves outside of the system. Their point of view, and let me draw a little man and label him chemistry. Chemistry stands outside of the system. Physics, their point of view, is from within the system. And here's why that makes a difference, is what signs do we give to these energies? So a chemist would say energy going in, well, that's energy that I'm losing. You see how the arrow's going away from him? So he would say this is negative, and energy out comes back to me, and so it's positive. A physicist sees it the other way around. Energy coming into the system is positive, and energy leaving the system is negative. And this makes a lot of sense if you just keep in mind these 2 point of views, okay? We are going to use the physics point of view, obviously, all right? But if you see this discrepancy, and it comes up in formulas, like when you're writing out a physics formula, and you need to know, oh, is that a plus sign or a minus sign there? You will see, if you Google it, that sometimes you'll find the wrong sign. Those are the chemists, all right? It's not just a blatant mistake, it's that they actually do it differently, because they'll put a minus where we'll put a plus, and vice versa. We are using this convention. Remember that. Energy in is positive, energy out is negative of the system. Energy transfer, that's what we're talking about here. And this is really important, actually. We're going to get into this. But energy can transfer in 2 different ways. There's 2 ways energy can transfer. The first is work, and the second is heat. That's it. In the whole universe, just 2 ways. And so we're going to talk about, there are going to be individual lectures in the future about work and about heat. So this is the introduction to those topics, okay? And it's important to notice that energy transfer is not a type of energy. Remember that we listed up here all the different forms of energy? Well, think of energy as something that a system has, right? Let's say there's a system and another system. Let me use red to represent the energy. Little bubble of energy. Let's say it has it. This could be our forms, like our potential, kinetic, and whatever, and it might have different forms. And this system might have forms. Heat and work are not forms of energy. It's not like we can point to a little bit of energy and say that is work. that little piece of energy that the system has. The system doesn't have work. Work are the arrows in this diagram, okay? Work and heat. They're like the ways that energy is transferred back and forth. Okay, that's an important distinction. Work and heat aren't something a system has. They're a way that the system transfers what it has. So I think that's where I'll leave it for right now. Like I said, there's a lot more. We're going to come back and continue on this topic. Thank you guys.